You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists. We're going to shine a light on our topics such as energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. Applications depend on certain or fixed capacity values to achieve their desired performance. However, ambient temperature, structural changes, or even component tolerances all play an important role. The required performance in the application can only be guaranteed if all phenomena that may occur are correctly taken into account. So today we are going to discuss an overview of the most important factors and how these can be reduced by using a different material or even external influences. Before we get started, we need to talk about the two types of MLCCs. Capacitors are constructed of Class 1 or Class 2 ceramics, and they vary in several aspects. For example, Class 1 ceramics are made of titanium dioxide, have permittivity between 10 and 500, a capacitance range of between 0.3 picofarad and 22 nanofarad, and a voltage range of between 10 to 50 volts. Their sizes are also between 0201 to 1812, have frequency dependency, but do not have voltage or temperature dependency or even aging. Class 2 ceramics are made of barium titanate. They have permittivity between 500 and 10,000 nanofarad and a voltage range between 6.3 and 100 volts. Their sizes also include 0201, but go up to 2220. Much like the Class 1, the Class 2 also has frequency dependency, but unlike Class 1, Class 2 does have voltage and temperature dependency and aging. The properties and tolerances of the different ceramic classes are defined by an IEC or an EIA coding. Depending on the application, a certain amount of capacitance needs to be available to achieve the desired performance in such applications as filters. This means that it is important to compare the properties of the individual components to ensure the desired behavior when used in the application. It should also be mentioned that the high capacitance MLCCs, the high capacitance is only available with the drawback of increased aging and therefore a greater loss of capacitance due to temperature and voltage. Next, let's define aging. So aging is a process in which certain properties change over time. Ferroelectric materials such as barium titanate are also subject to this process. And while they may not get wrinkles or gray hairs, the crystal structure of the dielectric changes with temperature and then also with time. This is considered aging, since the capacity changes, or more precisely, is reduced by this event. Another result of aging is the increase in the loss factor, which becomes steadily larger. Aging is usually described by a percentage loss of capacitance per decade of time. It is in the range of around 6% after 1,000 hours for X5R ceramics, and then roughly 2.5% after 1,000 hours for X7R ceramics per decade hours. After realigning the crystal lattice, such as by a temperature process that can be repeated as often as possible, aging leads to a loss of capacitance. The process of aging is logarithmic and decreasing with time, although it appears linear on charts when using logarithmic scales. So why does aging exist for barium titanate? Well, the permittivity of barium titanate is defined by the polarizability of the material. Further ferroelectric domains are formed by aging. The spontaneous polarization direction changes in such a way that not all dipoles can be polarized very well. The dipoles of two adjacent domains no longer point in the same direction. The result is the reduction of the capacitance. The solution? Reformation of the material. The effect of aging is influenced by time, temperature, and voltage. And since barium titanate is a ferroelectric material and, like a ferrite, has electrical domains, these domains divide with the factor time and thus reduce the capacitance. By tempering, the so-called preheating process, which is heating the material above the Curie temperature, the existing domains actually dissolve. Below the Curie temperature, the material then forms a new large domains again, which in turn results in a high capacity. The thermal movement in the crystal lattice caused by the annealing process prevents the dipoles from aligning completely when an electric field is applied, therefore reaching a kind of saturation. So how can aging be stopped? No, it's not some miracle cure on late-night television. The dielectric used in Class II MLCCs has ferroelectric properties. These material properties change when the Curie temperature is exceeded, much like with ferromagnetic materials. So above this temperature, the dielectric has a highly symmetrical cubic crystal structure. And then below the Curie temperature, the crystal structure has a less symmetrical, more tetragonal structure. The transition from the different phases, such as going from cubic to tetragonal, always results in a maximum value of permittivity over this temperature range. To achieve a stable state, the atoms in the crystal lattice move under the influence of thermal vibration for a long time, even after the dielectric has cooled down below the Curie temperature. More and more domains are formed. However, when the capacitor is heated to a temperature above the Curie temperature, aging takes place. So the capacity lost due to the aging is regained and aging again begins from the point at which the capacitor cools down. The temperature is around 125 degrees Celsius for barium titanate, and depending on how long the Curie temperature is exceeded, this results in the capacitance value that is set. According to the datasheet, the recommendation for preheating at 150 degrees Celsius is 1 hour. By this thermal treatment, the maximum 100% capacity of the component can be restored. So what does this mean for your application? In a real application which contains voltage and it's operated at a certain ambient temperature, a reduction in capacity over time needs to be accounted for and calculated in when using MLCCs. This is completely unavoidable, and it's caused by the base material used for Class II ceramics. It's now up to the design of the capacitor to compensate for this capacitance loss. A 100% test is performed after manufacture to ensure that all tolerances are met. Depending on storage time and storage conditions, these values may change over time. Due to the heat influence of the soldering process, the aging process is reset. In applications where stable capacitance values are required, aging must be considered, or a Class I MLCC must be used. If capacitors are used as output capacitors, such as switching regulators, the effect of aging can be best compensated for, as in this case, the capacitance fluctuations are in the low single-digit range and therefore have no negative effect on the function of the circuit. In conclusion, the aging is recorded at room temperature around 20 degrees Celsius, and it has around 0 volts as applied voltage. At room temperature and 0 degree volts, ceramic capacitors have almost no temperature, DC bias, and frequency influences that could influence aging. Below the Curie temperature and after applying a voltage, the existing ferroelectric properties polarize the molecules in a defined manner. The cubic structure becomes a tetragonal structure, which leads to a decrease in permittivity and thus in capacity. But now, what leads to aging? If the crystal structure of the ceramic is left at room temperature without load, randomly oriented domains are formed in which non-directional dipoles are formed, which have a negative influence on the permittivity. These randomly oriented domains tend to grow faster at first, and then they develop more slowly. Therefore, the loss of capacity is shown logarithmically. When a voltage is applied and the temperature is increased, the formation of randomly oriented domains slows down since the dipoles are aligned in a defined manner by the electric field. In practice, this means that aging, as discussed in our logarithmic scale, is really more of a worst-case scenario. Since the decrease in capacity via DC bias and temperature is significantly higher than the expected aging, this is assumed to be a fixed value. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note as we discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You are listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast.